Diffraction grating. Diffraction grating is an optical device which consists large number of slits. And so we can say that it is Fraunhofer diffraction at multiple slits. Now what is the grating and how many types are there? There are two types of gratings. One is called the transmission grating and the another one is reflection grating. Now the transmission gratings are made by scratching lines on transparent glass plate using the diamond knife. Lines are scratched on the transparent glass plate so that these lines can act like a opaque space. See, lines are opaque to the light. Light cannot pass through it. And the space between the lines called slits through which light can pass. But the width of the slit is comparable to the wavelength of light. Then only diffraction can take place when light passes through grating. Another type of grating is called the reflection grating. The reflection grating is made by inscribing lines on metallic surface or on reflecting glass surface. Such a lines are inscribed, engraved और अंकित की जाती है लाइंस अंकित की जाती है रिफ्लेक्टिंग सरफेस पे that makes reflection grating. So these are the two types of grating. In this lecture, we are going to consider transmission grating, which is having n number of slits, large number of slits, that is n number of slits it consists. So let's see first the diagram of that. In this diagram, as you can see, there are n number of slits. Let's say this one is slit S1, slit S2, slit S3, and the last slit is Sn. So S1 to Sn are n number of slits. These slits are parallel to each other and width of each slit is equals to A. All these slits are of equal width, which is A. And there is a space between these two slits. This is the space here between the two slits. And width of that space is B, small b. Then grating element is equals to A plus B. Generally, it is denoted by letter D. What you see in this diagram is this W, and the W is plane wavefront whose wavelength is lambda. When this plane wavefront is incident on this glass, on this grating, when the wavefront is incident on the grating, then according to Huygens principle, each and every point in each slit, every point in each slit act as a secondary source and emit secondary waves in all directions. That is as per Huygens theory. Those secondary waves which are starting from midpoint of each slit. Secondary waves which are starting from midpoint of each slit in a direction normal to the plane of the slit. Now plane of these slits, since these slits are parallel to each other and the plane of the slits is perpendicular to this page where I am writing. So I have shown this arrow. That arrow direction is normal to the plane of the slits. So those secondary waves which are traveling in a direction normal to the plane of slits are focused at point P naught. So n number of waves are reaching at point P naught, which are starting from the midpoint of every slit and traveling in a direction normal to the plane of slits. And those secondary waves which are traveling in a direction theta with normal to the plane of the slits. These secondary waves are traveling from midpoint of every slit in a direction theta with normal to the plane of the slits. This theta is angle between the secondary waves and normal to the plane of the slits. Such a secondary waves are focused at point, let's say P1. This is point P1. All secondary waves which are traveling in a direction theta with normal to the plane of the slits are focused at point P1. On the screen, this is the screen, we have 2 points P0 and P1. According to, we have studied last time, Fraunhofer diffraction from single slit. Like this is the single slit, where we assume that in these slits there are n number of small slits and each one emitting one phasor, and all these phasor are reaching at some certain point P1, and resultant amplitude of such a waves which are reaching at point P1 is equals to Em sin alpha upon alpha. But here is not a single slit. There are n number of slits here. So according to Fraunhofer diffraction at single slit, diffracted rays at an angle theta, all these diffracted rays from single slit at an angle theta are equivalent to single wave of amplitude Em sin alpha upon alpha. This is what we studied in Fraunhofer diffraction at a single slit. In other words, what we are saying that in a direction theta, one wave from midpoint of each slit is emitted. From the midpoint of each slit, one wave in a direction theta is emitted whose amplitude is Em sin alpha upon alpha, where alpha is equals to pi by lambda a sin theta. This theta is this theta over here. So हम लोग क्या समझ रहे हैं कि हर एक स्लिट उसके मिड पॉइंट से एक वेव एमिट कर रही है इन अ डायरेक्शन थीटा, जिसका एम्पलीट्यूड है Em sin alpha upon alpha. So at point P, n number of secondary waves reaching, which are emitted from midpoint of each slit, and each one is having amplitude Em sin alpha upon alpha. So n number of waves are reaching at point P1, and to find electric field distribution at point P1 or to find out intensity at point P1, we have to find path difference between these n number of waves. which are reaching at point P1. To find path difference between this n number of waves, we have to draw a normal. So this one is normal. And for convenience, let us consider only slit S1 and S2. Consider slit S1 and S2. Then the path difference between waves, secondary waves, starting from midpoints of each slit, of course S1 and S2, which are reaching at point is. What would be the path difference between such a secondary waves which are starting from midpoint of slit S1 and midpoint of slit S2, which is reaching at point P1. Now we know that the distance between the slit center of slit S1 to the center of slit S2, that distance is equals to A plus B, and the angle is theta, that is this angle is theta. And so path difference between the secondary waves which are starting from midpoint of slit S1 and S2 reaching at point P1 is A plus B sine theta. So the path difference is A plus B. This path difference is A plus B sine theta. If this is the path difference, then we know the relation between the path difference and the phase difference. So we can say that corresponding phase difference is 2 pi by lambda A plus B sine theta. This is the corresponding phase difference between the secondary waves which are starting from S1 and S2, which are reaching at point P1. And let us assume that this is equals to 2 beta. If that is 2 beta, then obviously beta is equals to pi by lambda A plus B sine theta. So this is the beta. And we know what is the alpha. Alpha is this, pi by lambda A sine theta. Then let us find path difference between secondary waves starting from slits S1 and Sn, which are reaching at point P1. So now we are considering the slit S1 and slit Sn, and the path difference between them is equals to this length. This is the path difference. Now the distance between the slit S1 and Sn is n times A plus B, and the angle over here is theta. And so this path difference is equals to n times A plus B sine theta. So path difference is n times A plus B sine theta. And if that is the path difference, then corresponding phase difference is 2 pi by lambda n times A plus B sine theta, and that would be equals to 2n beta, because this 2 pi by lambda A plus sine theta we assume equals to 2 beta. So 2 pi by lambda n times a plus b sine theta is equals to 2n beta. Now n slits are there and there are n number of waves. So from each slit there are n number of slits. From each slit you can say we get one secondary wave, or you can say one phasor whose amplitude is E1. From, from slit 2 we get the phasor E2, and that would be equals to up to En, which is equals to Em sine alpha upon alpha, because each wave has amplitude Em sine alpha upon alpha. Then we have to find resultant of this, because at the point P1 we are getting n number of phasors, E1, E2 up to En. These n number of phasors, or you can say n number of secondary waves reaching at point P1, and we need to find what would be resultant amplitude at point P1. And this resultant amplitude can be found by vector addition method. Resultant amplitude is found by vector addition method. So in this case, using the vector addition method, we can find the resultant amplitude at point P1. So n number of phases reaching, or n number of secondary waves are reaching at point P1. Let's say this one, this is the arc. So n number of phases will form a arc in which this is the phasor E1, this is the phasor E2, and the phase difference between these two neighboring phasors, or these two neighboring secondary wave, is equals to 2 pi by lambda a plus b sine theta, which is equals to, we assume that is equals to 2 beta. So phase difference between the E1 and E2 is 2 beta. Like that, there are n number of these phasors or secondary waves. The phase difference between the consecutive secondary waves is 2 beta, and this one is, last one is the nth number phasor. So this is forming the arc, and resultant of this arc is the chord. So we have to draw the chord. This is the chord, which is the resultant of this arc, and we can call it, this is the resultant amplitude ER. So we get the resultant amplitude ER from the chord. Let's say this point is A and this point is B. Now this arc AB, is a part of the circle. This arc is the part of the circle whose center is, let's say, at point C. Arc AB is the part of the circle whose center is at point C. Then this CB and this CA are the radius of that circle. So this is equals to R. Let us write that AB is chord and this CB is equals to CA, which is the radius of the circle whose part is this arc. Then we know that the total phase difference, that is the phase difference between the first secondary wave and the last secondary wave, or the first phasor and the last phasor, is 2n beta. Okay, the part difference between the S1 and Sn slit is this. Corresponding phase difference is 2 pi by lambda n into a plus b sin theta, which is equals to 2n beta. So this angle ACM is equals to 2n beta. So the angle this angle is ACB is equals to 2n beta. That angle is equals to 2n beta. Then what I am going to do is I am going to draw a normal on the chord. So from the point C such that it will divide the chord into two equal parts. So let us say this point is D. So that this is equals to ER by 2 and this is also equals to ER by 2. So in this case AD is equals to DB is equals to ER upon 2. Then this angle over here is n beta. Similarly, this angle is also equals to n beta. One more line I am drawing which will join center C and the E1. And let's say that point is N. Then what is the angle ACM? This angle is equals to 2 beta. That angle is equals to 2 beta. One more line which will divide this E1 into two parts. Let us say that point is O. So this AO is equals to OM and that is equals to E1 by 2. So length of OM is equals to length of AO and that is equals to E1 by 2. And this angle is equals to beta. Then we can find sine beta from the angle ACO. ACO is equals to beta. And therefore, this sine beta is equals to AO upon AC. AO is E1 by 2 and AC is R. So sine beta is equals to E1 upon 2R and hence R is equals to E1 upon 2 sine beta. This is equation 1. Then we are going to consider the triangle ACB, which is equals to n beta. And from this, sine of n beta is equals to ER upon 2R. This is ER by 2 and radius is R. So sine of n beta is equals to ER upon 2R. Therefore, R is equals to ER upon 2 sine n beta. and this is equation 2. Then from equation 1 and 2, you can see the left hand side is R, so right hand side should be same. So from equation 1 and equation 2, we can write this ER upon 2 sine n beta is equals to E1 upon 2 sine beta. Therefore, ER is equals to E1 sine of n beta upon sine beta. But this E1 is nothing but Em sine alpha upon alpha into sine of n beta upon sine beta. Since E1 is equals to Em sine alpha upon alpha. Now this equation is for resultant amplitude. This equation gives us resultant amplitude. If this is the resultant amplitude, then what is the resultant intensity? Then resultant intensity is equals to IR, which is equals to Em square sine square alpha upon alpha square into sine square n beta upon sine square beta. So that is the equation for resultant intensity. Now this equation, this intensity equation consists two parts. Two components. The first component is Em square sine square alpha upon alpha square, and this is diffraction term or a diffraction component, and this is because of due to diffraction from single slit. And second component is sine square beta upon sine square n beta upon sine square beta. This is sine square n beta upon sine square beta, and this is interference term. And this is because interference between n number of secondary waves emitted from n number of slits. So from this we can understand that the resultant intensity is the combination of diffraction effect and the interference effect. So when there is a diffraction from the grating, the resultant which we get, it is a combination of diffraction due to single slit and interference between the secondary waves, n number of secondary waves emitted from n number of slits. So resultant intensity is a combination of diffraction effect and interference effect. Then let's find the condition for principal maxima. We are going to find now the condition for principal maxima. For principal maxima, we know the intensity IR, resultant intensity is Em square sin square alpha upon alpha square sin square n beta upon sin square beta. This is the resultant intensity. And for principal maxima, this IR should be maximum. And for IR to be maximum, this term sin square n beta upon sin square beta should be maximum. And you will get this maximum only when this sin beta is minimum. And minimum means this sin beta should be 0. For this term to be maximum, this sin beta should be minimum, that is 0. This sin beta is 0 only when the beta is equals to plus minus n pi, where n starts from 0, 1, etc. If beta is plus minus n pi, then this term, let us consider only, no, let us not consider square, consider only the term sin n beta upon sin beta, that is 0 upon 0 when beta is plus minus n pi. And 0 upon 0 means this is indeterminate. We can't find that. To find it, we have to use L'Hospital's rule. To solve it, L'Hospital rule is used. And according to L'Hospital's rule, limit of beta tends to plus minus n pi sine of n beta upon sine beta is equals to limit of beta tends to plus minus n pi. We have to take the derivative of denominator and numerator, that is d by d beta of sine n beta divided by d by d beta of sine beta, which is equals to n cos n beta divided by cos beta, which is equals to n cos of n, beta is plus minus n pi divided by cos of beta, which is plus minus n pi, and this is equals to plus minus n. So sin n beta upon sin beta is equals to plus minus n, and we have this intensity relation. If that is equals to n, then the resultant intensity IR is equals to Em square sin square alpha upon alpha square into n square. This is sin square n beta upon sin square beta. We know the value of sin n beta by sin beta, which is n. So the square of that. Or you can say that the resultant intensity is directly proportional to square of n, square of number of slits. Now to get this intensity maximum, we assume that this beta should be equals to plus minus n pi. But you know the beta. We assume the beta is equals to pi by lambda a plus b sine theta. So this pi cancels with this pi, and what you get is a plus b sine theta is equals to plus minus n pi. This a plus b is d. So d sine theta is equals to n lambda. Let us forget about this plus minus. It is there. So this is the grating equation for the principal maxima. D sine theta is equals to n lambda. Then find condition for minima. For minima, this term sin n beta upon sin beta should be minimum, and this would be minimum when this sin n beta is equals to 0. But sin beta cannot be 0, because if sin beta is 0, that is the condition for principal maxima. So sin beta should not be 0, but sin n beta should be 0. And you get sin n beta 0 only when this n beta is equals to plus minus n pi. And that is equals to n times, and beta is pi by lambda a plus b sine theta. So in this pi cancels with this pi, and you get n times a plus b sine theta is equals to plus minus n lambda, or you can write this nd sine theta is equals to n lambda. So this is the condition for minima. Nd sine theta is equals to n lambda, but this n cannot have values like 0, 1, 2 up to n, then 2n up to nn. This n can have any values other than this, because if the n has these values, then we get the principal maxima. So this n cannot have these values. It can have any other values than this. Then you get principal maxima. Now let us see the graph of this principal maxima and minima. Let us find the graph. This is the graph. And in this case, this is the diffraction effect. That is diffraction due to single slit. This is the intensity axis, which is equals to Em square sine square alpha upon alpha square, and this is the principal maxima due to single slit. Then there is an interference effect. This one is interference effect. Interference effect, maximum intensity is sine square n beta upon sine square beta, and whose graph is this. And actually, the resultant is combination of diffraction and interference effect, which is equals to this Em square sine square alpha alpha square sine square n beta upon sine square beta. And this is the diffraction pattern from the grating. So these are the principal maximas That is here n equals to 0. For this n equals to 1. For this n equals to 2. Similarly, this side also. On either side, you get principal maximas. All these are the principal maximas, which we call zeroth order, first order, second order, third order, and so on. And between two principal maximas, between any two principal maximas, in between there are n minus 1 number of minimas and n minus 2 number of secondary maximas. But intensity of secondary maxima is so less that we can't see those secondary maxima. We see only prime principal maximas like zero order, first order, and so on.